Welcome to our comprehensive tutorial on the Transformers AutoTokenizer, where we'll explore one of the most fundamental components of modern NLP. We've organized this into 6 chapters. Chapter 1, Getting Started and Basic Operations, covers loading pre-trained tokenizers and basic tokenization. Chapter 2, Batch Processing and Advanced Encoding, teaches efficient multi-text processing with padding and truncation. Chapter 3, Model Preparation and Special Tokens, explores CLS, SEP, and PAD tokens for transformer models. Chapter 4, Vocabulary Management and Customization, shows how to inspect vocabularies and add custom tokens. Chapter 5, Saving, Loading, and Special Use Cases, covers production deployment and multilingual scenarios. Finally, Chapter 6, Chat Templates and Conversational AI, teaches how to format conversations for chat-based models. Welcome to Chapter 1, where we're diving into getting started with tokenization and basic tokenization operations. Let me break down what we'll be covering today. We'll learn how to load pre-trained tokenizers using from pre-trained, work with basic tokenization methods like tokenize and encode, convert between tokens and IDs, decode token IDs back to readable text, explore tokenizer vocabularies, and understand how subword tokenization works. Let's begin by looking at the tokenization pipeline architecture to understand what's happening under the hood. Here we have a visualization of the tokenization pipeline architecture. This diagram shows us the complete flow of how text gets processed through tokenization. You can see how raw text moves through various stages, from initial preprocessing through tokenization, then conversion to IDs, and finally how those IDs can be decoded back to text. This gives us a clear mental model of the entire process we'll be working with. Now let's set up our environment and import the necessary libraries. This is always our first step when working with tokenizers. Here we're importing all the essential libraries we'll need. We're bringing an AutoTokenizer from Transformers, which is our main tool for working with tokenizers. We're also importing NumPy for numerical operations, Matplotlib and Seaborn for creating visualizations, and Counter from collections to analyze token frequencies. I'm setting up the visualization style to make our plots look clean and professional. This gives us everything we need to explore tokenization in depth. Perfect! Our setup is complete, and we're ready to explore tokenization. Now we move to Section 1, loading a pre-trained tokenizer with from pre-trained. This method is your gateway to using any pre-trained tokenizer from the Hugging Face Model Hub. It's incredibly powerful because it gives you instant access to tokenizers that have been trained on massive datasets. Let's load a BERT tokenizer and explore its properties. We're using BERT base uncased here, which is one of the most commonly used tokenizers. I'm loading it with AutoTokenizer from pretrained, and then we'll verify that it loaded correctly by checking some assertions. We want to make sure the tokenizer exists, that it has the expected maximum length of 512 tokens, and then we'll examine its key properties like the tokenizer type, vocabulary size, and special tokens. Excellent, we've successfully loaded a BERT tokenizer fast. Notice it has a model max length of 512 tokens, which is standard for BERT models. The vocabulary contains 30,522 tokens, and we can see the special tokens like PAD with ID 0 and UNK for unknown tokens with ID 100. These special tokens play crucial roles in how BERT processes text. Here's a handy reference table showing all the parameters you can use with from pretrained. The most important one is the model name or path, which is required. You can control whether to use the fast Rust-based tokenizer, specify a cache directory, force RAID downloading, or work with only local files. These options give you flexibility in how you load and manage tokenizers. Let's compare different tokenizers to see how they vary. I'll load 3 popular tokenizers, BERT base uncased, GPT-2, and Roberta base, and compare their characteristics. This will help us understand that different models use different tokenization strategies and have different vocabulary sizes and maximum lengths. Interesting, look at these differences. BERT uses a vocabulary of about 30,000 tokens with a max length of 512. GPT-2 has a much larger vocabulary of over 50,000 tokens and supports sequences up to 1024 tokens. Roberta, which is based on BERT, has a similar vocabulary size to GPT-2, but keeps the 512 token limit. These differences reflect the design choices and intended use cases of each model. Now let's explore basic tokenization with the tokenize method. This is the first step in the tokenization pipeline, where we convert text into a list of tokens or subwords. This is fundamental to understanding how transformers process text. Let's tokenize a simple sentence and see what happens. We'll take "Hello, how are you doing today?" and break it down into tokens. The tokenize method will split this into individual tokens and will verify that we get a list of strings back. Perfect! Our sentence has been split into 8 tokens. Notice how punctuation marks like the comma and question mark become separate tokens. Also, because we're using BERT base uncased, everything is converted to lowercase. The tokenizer treats each word and punctuation mark as a distinct unit. Now let's understand subword tokenization better. BERT uses word piece tokenization, which can split unknown or rare words into smaller subword units. This diagram shows how this process works. When the tokenizer encounters a word that's not in its vocabulary, it breaks it down into smaller pieces that it does recognize. The double hash prefix indicates tokens that continue a word rather than starting a new one. Let's see subword tokenization in action with some interesting examples. I'll test various words including tokenization, unbelievably, preprocessing, and even something ridiculous like supercalifragilisticexpialidocious. We'll see how the tokenizer handles each one and whether it splits them into subwords. Fascinating results! Look how tokenization splits into token and hashization. The word unbelievably gets broken down into 5 pieces with those double hash prefixes showing continuation. Even our longest word, supercalifragilisticexpialidocious, gets successfully tokenized into 11 subword pieces. This is the power of subword tokenization. It can handle any word, even ones it's never seen before, by breaking them into known components. Now we'll learn about encoding text to token IDs with the encode method. This combines tokenization and conversion to IDs in one step, and importantly, it also adds special tokens by default. These special tokens help the model understand the structure of the input. Let's encode some text and examine the token IDs. When we encode, natural language processing is fascinating. We'll see that special tokens are automatically added. The CLS token at the beginning and SEP token at the end are crucial for BERT's understanding of the text boundaries. Great, our text has been encoded into 8 token IDs. Notice that the first token is 101, which is the CLS token, and the last is 102, which is the SEP token. These special tokens frame our actual content. The model uses CLS for classification tasks and SEP to mark the end of a sequence. Here's a comprehensive reference table for the encode method parameters. You can control whether to add special tokens, apply padding or truncation, set maximum lengths, and specify the output format. Each parameter affects how your text is processed and what the final output looks like. Let's explore different encoding configurations to see how these parameters work in practice. We'll test the same sentence with different settings, including with and without special tokens, with padding, and with truncation. This will show you the flexibility you have when encoding text. Look at these different results. Configuration 1 with special tokens gives us 11 tokens. Without special tokens in config 2, we get 9 tokens, exactly 2 fewer. Config 3 pads to exactly 20 tokens by adding zeros at the end. Config 4 truncates to keep within 10 tokens while preserving the special tokens. These options let you prepare text exactly as your model needs it. Now let's learn about decoding token IDs back to text with the decode method. This reverses the encoding process and is essential for understanding what your model is producing. We'll demonstrate the full encode-decode cycle. Starting with machine learning is amazing, we'll encode it to IDs and then decode it back. We'll try decoding both with and without special tokens to see the difference. Perfect reconstruction. When we decode with special tokens visible, we can see the CLS and SEP tokens in the output. When we skip special tokens, we get back our original text in lowercase. This shows that the tokenization process is reversible, and we don't lose information when converting to IDs and back. Now let's test reconstruction with complex text containing subwords. We'll use a sentence with sophisticated vocabulary to see if the tokenizer can perfectly reconstruct text that gets split into subword tokens. Excellent, even though words like unbelievably and preprocessing were split into multiple subword tokens, the decoder perfectly reconstructs the original text. The tokenizer remembers how to merge those double hash prefix tokens back into complete words. Sometimes you need fine-grained control over the conversion process. Let's explore manual token to ID conversion. The tokenizer provides methods for converting between tokens and IDs step by step, giving you complete control over the process. We'll walk through the manual conversion pipeline step by step. First, we tokenize the text into tokens, then convert those tokens to IDs, and finally convert the IDs back to tokens. This shows you exactly what's happening at each stage of the process. Perfect round-trip conversion. We started with tokens, converted them to IDs, and got back exactly the same tokens. This demonstrates that the conversion process is completely reversible and deterministic. Let's examine the special token IDs in detail. BERT has several special tokens, each with a specific purpose. We'll look at CLS for classification, SEP for separation, MASK for masked language modeling, PAD for padding, and UNK for unknown tokens. Here are all the special token IDs. Notice they all have low ID numbers. CLS is 101, SEP is 102, MASK is 103, PAD is 0, and UNK is 100. These low IDs make them easy for the model to recognize. When we convert these IDs back to tokens, we get the exact same special token representations. Now let's explore the vocabulary with GetVocab. The vocabulary is the complete mapping between all tokens and their IDs. Understanding the vocabulary helps you know what your tokenizer can represent. Let's get the vocabulary and examine its structure. We'll check the total size, verify it's a dictionary, and look up some sample words to see their token IDs. The BERT vocabulary contains exactly 30,522 tokens stored as a dictionary. We can see common words like hello and world have their own token IDs. Words like artificial and intelligence are also in the vocabulary. Notice the subword tokens like hashing and hashly that are used to build larger words. Let's analyze the composition of the vocabulary. We'll count how many subword tokens, special tokens, single characters, and numbers are in the vocabulary. This gives us insight into how the vocabulary is structured. Interesting breakdown. About 19% of the vocabulary consists of subword tokens with the double hash prefix. There are 999 special tokens, which BERT uses for various purposes. We also have nearly 1,000 single character tokens and 881 pure number tokens. This diverse vocabulary allows BERT to handle a wide variety of text efficiently. Now let's visualize token distribution with a real paragraph. We'll analyze how text is tokenized and look at the distribution of tokens to understand compression and tokenization patterns. We'll tokenize a paragraph about natural language processing and gather statistics about how it's processed. This will show us the relationship between characters, words, and tokens. Great analysis. Our 423-character paragraph with about 60 words becomes 72 tokens. We have 49 unique tokens, with 68 whole word tokens and only 4 subword tokens. The compression ratio of 5.88 characters per token shows how efficiently tokenization represents text. Now I'll create visualizations to show the token distribution patterns. We'll look at the most frequent tokens, the distribution between whole words and subwords, token length distribution, and how token IDs are distributed. These visualizations reveal interesting patterns. The bar chart shows which tokens appear most frequently in our text. The pie chart confirms that most tokens are whole words rather than subwords. The token length histogram shows most tokens are 3 to 7 characters long with a mean around 5. The token ID distribution shows we're using mostly common tokens with lower IDs, which makes sense for standard English text. Let's look at a real-world application by processing multiple sentences with different lengths. This simulates how you might handle batches of text in practice. We'll process several sentences of varying lengths and complexity. For each one, we'll measure the character count, token count, ID count, and compression ratio. This shows how tokenization efficiency varies with different types of text. Notice the patterns here. Shorter, simpler sentences have lower compression ratios, around 3.5 to 4.4 characters per token. But our longest, most complex sentence about artificial intelligence achieves 6.75 characters per token. This shows that tokenization is more efficient with longer, more sophisticated text. Also note that ID count is always token count plus 2, accounting for the CLS and SEP special tokens. Now let's explore handling long sequences. This is a crucial skill because models have maximum sequence lengths, and you need to know how to handle text that exceeds these limits. We'll create a very long text by repeating a sentence 100 times, then see what happens when we tokenize it. We'll try encoding without truncation, which will exceed BERT's maximum length, then with truncation to stay within limits, and finally we'll look at padding short text. Important lessons here. Without truncation, our text produces 600 tokens, which exceeds BERT's 512 limit and would cause errors if fed to the model. With truncation, we get exactly 512 tokens, safely within limits. For padding, our short text becomes 50 tokens with 46 pad tokens filling the rest. These techniques are essential for handling real-world text of varying lengths. Let's examine common pitfalls and best practices. Understanding these will save you from bugs and confusion. First pitfall: special tokens affect sequence length. The tokenize method doesn't add special tokens, but encode does by default. This two-token difference can cause confusion. Second pitfall: BERT uncased converts everything to lowercase, so hello world and hello world produce identical token IDs. Always test your assumptions. These pitfalls are easy to miss, but important to understand. The two-token difference from special tokens can throw off your length calculations, and the case insensitivity of BERT uncased means it treats hello world and hello world identically. The best practice is always to verify your tokenization assumptions with actual tests. Here's our comprehensive summary and key takeaways. We've covered all the essential tokenization methods and best practices you need to work effectively with transformers. Congratulations! You've completed Chapter 1. Let's review everything you've learned. You now know how to load pre-trained tokenizers, perform basic tokenization operations, convert between tokens and IDs, decode tokens back to text, explore vocabularies, handle subword tokenization, and manage sequence lengths. These are the fundamental skills for working with any transformer model. Excellent work! You've mastered all the foundational tokenization concepts. You're now ready to move on to Chapter 2, where we'll explore advanced encoding techniques. Great job! And that concludes our comprehensive exploration of tokenization basics. Thank you for following along. Welcome to Chapter 2, where we're diving into batch processing and advanced encoding with the AutoTokenizer. In this chapter, we're going to master how to process multiple text sequences efficiently, understand padding and truncation strategies, work with attention masks and token type IDs, decode tokenized sequences back to text, and configure advanced tokenization settings. These are essential skills for working with transformer models in production. Let me show you the architecture overview. This diagram illustrates how batch processing flows through the tokenization pipeline. Notice how multiple text inputs are processed in parallel, with padding and truncation applied uniformly across the batch to create tensors that can be efficiently processed by our models. Let's start with the setup and initialization section. First, I'll import all the necessary libraries and initialize our tokenizer. We're using BERT-base uncased here, which is a great general-purpose tokenizer. Let's see what properties this tokenizer has. Perfect. We can see we're using a BERT tokenizer fast tokenizer with a vocabulary size of 30,522 tokens. The model can handle sequences up to 512 tokens. Notice how the padding token is represented as pad with an ID of 0, and we have all the special tokens defined, including UNK for unknown tokens, SEP for separation, CLS for classification, and mask for masked language modeling. Now let's explore Part 1, the Encode+ method. This is a powerful method that provides comprehensive encoding for a single sequence. Unlike the basic encode method, Encode+ returns not just token IDs, but also attention masks and token type IDs, which are crucial for transformer models. Let's see Encode+ in action. I'll encode a simple sentence and examine all the metadata it returns. Excellent! We can see that Encode+ returns 3 key arrays. The input IDs are the actual token representations. The attention mask shows which tokens are real versus padding, with all ones here since we have no padding. And the token type IDs are all zeros because this is a single sentence. Notice how all 3 arrays have the same length of 10 tokens, and the system automatically added CLS and SEP tokens. Let me show you another diagram that explains these token components in more detail. Here you can see how each component serves a specific purpose in the model's understanding of the input. Now let's decode these tokens to understand the exact mapping between our text and the token IDs. This will help us see how the tokenizer breaks down our sentence. Perfect! We can clearly see the structure now. Position 0 has the CLS token with ID 101, which marks the beginning of the sequence. Then we have our actual words. Notice how hello became lowercase since we're using an uncased tokenizer. The punctuation marks are treated as separate tokens, and finally, we have the SEP token at position 9 with ID 102. The attention mask is all ones because every token is a real token, not padding, and the type IDs are all zeros for a single sentence. Let's explore padding and truncation in Encode+. These are critical features when preparing data for models. I'll demonstrate different padding strategies. First, let's see what happens with a short text when we apply various padding options. Great demonstration of padding behavior. Without padding, we get just 4 tokens for our short hello text. When we pad to 20 tokens, the tokenizer adds 16 padding tokens, all with ID 0. Notice how the attention mask correctly identifies real tokens with 1 and padding tokens with 0. This is crucial because the model needs to know which tokens to ignore during processing. Now let's test truncation with a very long text. I'll create a text with 100 repetitions of the word word and see how truncation handles it. Excellent! Without truncation, our long text expands to 102 tokens, which would exceed many model limits. With truncation set to max length 15, it cuts the sequence to exactly 15 tokens. When we combine both padding and truncation with max length 20, we get exactly 20 tokens, and since our truncated text fills all 20 positions, we see 20 real tokens with no padding needed. Moving on to Part 2, Batch Encode+ for processing multiple sequences. This is where tokenization becomes really powerful for production use. When working with batches, the tokenizer automatically handles padding to create uniform length sequences. Let me encode 3 texts of different lengths and see how batch processing handles them automatically. Perfect! We have 3 sequences of very different original lengths. The batch encoder automatically padded all sequences to 21 tokens, which is the length of the longest sequence. Sequence 0 only has 5 real tokens and 16 padding tokens. Sequence 1 has 12 real tokens and 9 padding tokens. Sequence 2, being the longest, has all 21 real tokens with no padding. This uniform length is essential for batch processing in neural networks. Let me visualize these attention masks to really show how padding works in batches. This visualization clearly shows the attention mask patterns. Green represents real tokens with value 1, while red represents padding tokens with value 0. You can see how the short text has mostly padding, the medium text has moderate padding, and the longest text has no padding at all. This visual representation helps understand why attention masks are so important. They tell the model exactly which tokens to pay attention to. Here's a quick reference table for batch processing parameters. These parameters give you fine control over how your text is processed. Now let me show you a comprehensive table of all the batch processing parameters and their effects. This is your reference guide for configuring tokenization. Let's test different padding strategies to see how they affect the output. I'll use 3 texts of varying lengths and apply different padding configurations. Excellent demonstration of padding flexibility. With padding set to longest, all sequences are padded to 12 tokens, matching the longest sequence. With max length set to 25, all sequences are padded to exactly 25 tokens regardless of content. With no padding, we get the natural lengths of 4, 6, and 12 tokens. This flexibility allows you to optimize for your specific use case. Now part 3, batch decode for converting token IDs back to text. This is essential for understanding what your model is processing and for generating human-readable outputs. Let's decode our batch results and compare with and without special tokens. Perfect demonstration of decoding options. With special tokens included, we see everything including CLS, SEP, and PAD tokens, which shows us exactly what the model sees. When we skip special tokens, we get clean, human-readable text that matches our original input. This is crucial for presenting results to users or debugging your tokenization pipeline. Let's compare the original texts with the decoded versions to verify accuracy. Excellent, we have perfect similarity scores of 100% for all texts when accounting for lowercase conversion. This confirms that tokenization and decoding are lossless operations for the actual content. The only change is the lowercase transformation, which is expected with an uncased tokenizer. Part 4 covers the pad method, which allows post-processing padding. This is useful when you need to adjust padding after initial encoding, perhaps when combining batches or preparing for a model with specific requirements. Let me demonstrate the pad method by first encoding without padding, then applying padding afterwards. Great, we started with sequences of 3, 4, and 9 tokens. After applying padding to longest, all sequences are now 9 tokens, matching the longest sequence. When we pad to a specific max length of 30, all sequences expand to exactly 30 tokens. The warning message reminds us that using the call method directly is more efficient than separate encoding and padding steps. Let me visualize the padding distribution to show the efficiency implications of different padding strategies. This visualization reveals important insights. The average padding is 44.4%, which is reasonable. The bar chart shows how real tokens and padding tokens stack up for each sequence. The padding efficiency chart uses color coding, green for efficient padding under 30%, yellow for moderate, and red for inefficient over 60%. The most efficient strategy would be to pad to 9 tokens, the length of the longest sequence, to minimize wasted computation. Part 5 covers handling sentence pairs, which is crucial for many NLP tasks like question answering and textual entailment. The tokenizer uses special tokens and token type IDs to distinguish between the two sentences. Let's encode a question-answer pair and examine how the tokenizer handles the separation between them. Fascinating structure here. The tokenizer uses token type IDs to distinguish between the question and the context. Everything before the first SEP, token at position 8, belongs to the question with type ID 0. After that, from position 9 to 19, we have the context with type ID 1. The second SEP token at position 19 marks the end of the context. This clear separation allows models like BERT to understand the relationship between the two text segments. Now let's process multiple question-answer pairs in a batch to see how this scales. Perfect batch processing of sentence pairs. Each pair maintains the same structure with type 0 tokens for questions and type 1 tokens for contexts. All 3 pairs show 8 tokens for questions and 10 tokens for contexts, demonstrating consistent tokenization patterns. This uniformity is crucial for training and inference with question-answering models. Part 6 covers returning tensors for deep learning frameworks. Let's see how we can get outputs in different formats suitable for PyTorch, NumPy, or plain Python. I'll encode the same texts and return them in different formats to show the flexibility of the tokenizer. Excellent demonstration of output flexibility. With return tensors set to none, we get Python lists which are simple and lightweight. With PT, we get PyTorch tensors on CPU, ready for model inference. With NP, we get NumPy arrays with int64d type. All formats maintain the same shape of 3 by 6, representing 3 sequences of 6 tokens each. Choose the format that matches your downstream processing needs. Part 7 explores advanced configuration and optimization. Let's look at different truncation strategies for handling long texts. Let me test different truncation strategies with long question and answer pairs. Great results showing how different strategies handle truncation. The longest first strategy gives us exactly 30 tokens by truncating from the longest sequence first. The only first and only second strategies each process just one part of the pair, resulting in 22 tokens each. These options give you fine control over what information to preserve when dealing with length constraints. Now let's run a performance comparison with different batch sizes to understand the efficiency implications. Fascinating performance results. We can see that batch size 1 takes the longest at about 0.04 seconds, while larger batch sizes dramatically improve throughput. The throughput chart shows sequences per second increasing with batch size. The optimal batch size for this dataset appears to be 100, maximizing throughput. This demonstrates why batching is so important for efficient processing. Let's look at a practical example, building a question-answering pipeline. This brings together everything we've learned. I'll simulate a QA dataset and process it with optimal settings for a question-answering model. Excellent QA batch encoding. We have input tensors of shape 3 by 128, perfect for model input. Each QA pair shows the correct token distribution between questions and contexts. QA pair 1 has 7 question tokens and 17 context tokens. QA pair 2 has 8 question tokens and 20 context tokens. QA pair 3 has 7 question tokens and 17 context tokens. The assertion confirms that our token counts are consistent. This batch is now ready for model inference. Let me create a comprehensive visualization of the token analysis for our QA pairs. These visualizations provide deep insights into our QA tokenization. The token ratio chart shows questions typically use about 30% of tokens, while contexts use 70%. The padding overhead is very high at 81.3% average because we're using a fixed max length of 128 for relatively short texts. The attention mask heat map shows the active regions in green and padding in red. The token type ID heat map clearly distinguishes questions in blue from contexts in red. Based on this analysis, I'd recommend using dynamic padding or reducing max length to improve efficiency. Here's a best practices summary covering all the key points we've learned about padding strategies, truncation guidelines, performance tips, and common pitfalls to avoid. Finally, let me create a comprehensive function that implements all the best practices we've discussed. This function will process a batch optimally and return useful statistics. Perfect! Our optimized batch processing function successfully handled the test batch. We achieved a padding percentage of 41.7%, which is reasonable for texts of varying lengths. The function used padding equals longest to minimize waste, truncation equals true for safety, and returned PyTorch tensors ready for model inference. All assertions pass, confirming correct batch size and shape consistency. This function encapsulates all the best practices we've covered and can be used as a template for your own tokenization pipelines. That's all for Chapter 2. We've covered comprehensive batch processing with AutoTokenizer, from basic encoding to advanced optimization strategies. Thank you for learning with me. Welcome to Chapter 3, where we'll master model preparation and special tokens. These are fundamental concepts that you'll use in every transformer project. We're going to explore how to properly prepare inputs for transformer models, understand the role of special tokens, and learn to work with token type IDs and attention masks. We'll also discover how to handle custom special tokens for specialized tasks. This knowledge is essential for working with any transformer model. Let's look at this special token processing architecture diagram. This shows us the complete flow of how text gets transformed into model-ready inputs. Notice how raw text comes in on the left, goes through tokenization where special tokens like CLS and SEP get added, then gets converted to token IDs, and finally we generate the attention masks and token type IDs. This entire pipeline is what prepares our text for the transformer model. Now let's set up our environment and import the necessary libraries. We're bringing in the Transformers library for tokenization, Torch for tensor operations, and Matplotlib and Seaborn for creating visualizations. I'm also initializing a BERT-based uncased tokenizer, which we'll use throughout this chapter to explore special token handling. Great, our tokenizer is loaded successfully. We're using the BERT tokenizer fast, which is the optimized version of the BERT tokenizer. Notice our vocabulary size is 30,522 tokens. This includes all the regular tokens plus the special tokens we'll be exploring. Let's dive into understanding special tokens. These are reserved symbols that help models understand the structure of our input sequences. They're not part of the original text, but provide crucial metadata that tells the model where sentences begin and end, where to pay attention, and how to handle padding. Now I'll explore the built-in special tokens in BERT. Every BERT model comes with 5 essential special tokens. The CLS token marks the beginning of a sequence, SEP separates sentences or marks the end, PAD is used for padding shorter sequences, UNK represents unknown tokens not in our vocabulary, and mask is used for masked language modeling. Let me also verify that these special tokens are treated as single units during tokenization. Perfect, you can see each special token has its own unique ID. CLS is 101, SEP is 102, PAD is 0, UNK is 100, and mask is 103. These IDs are reserved and consistent across all BERT models. Notice in our tokenization test that CLS, SEP, and PAD are each preserved as single tokens, exactly as they should be. This is crucial because we don't want these special markers to be split into subwords. Let's explore Prepare for Model, which is the most comprehensive method for input preparation. This method handles everything we need, adding special tokens like CLS and SEP, padding sequences to a specified length, truncating if needed, creating attention masks to tell the model which tokens to pay attention to, and generating token type IDs for sentence pairs. I'm going to demonstrate the basic usage of Prepare for Model. We'll start with a simple sentence, tokenize it, convert to IDs, and then prepare it with different configurations. First, I'll show basic preparation without padding, then I'll show how padding works when we specify a max length. Excellent, look at how the basic preparation automatically adds the CLS token at the beginning with ID 101, and the SEP token at the end with ID 102. The attention mask is all ones because every token is real. When we add padding to length 15, notice how pad tokens with ID 0 are added, and the attention mask shows zeros for these padding positions. This tells the model to ignore those padded positions during processing. Here's a detailed parameter reference table for Prepare for Model. Each parameter controls a different aspect of the preparation process. The IDS parameter is your base token sequence. Pair IDS creates sentence pairs, add special tokens controls whether to add CLS and SEP, padding strategy determines how to pad, truncation controls length limits, max length sets the target size, and return tensors determines the output format. Now let's see how Prepare for Model handles sentence pairs, which is crucial for tasks like question answering or natural language inference. I'll prepare 2 related sentences and show how the tokenizer creates the proper structure with token type IDs to distinguish between them. Look at this beautiful structure. The tokenizer has created a single sequence with both sentences separated by SEP tokens. The token type IDs are particularly important here. They're all zeros for the first sentence including its SEP token, then switch to ones for the second sentence. This is how BERT models distinguish between the 2 input segments. The decoded sequence clearly shows the structure with CLS at the start, first sentence, SEP separator, second sentence, another SEP, and then padding. Let me visualize different padding strategies to make this clearer. We'll see how sequences look with no padding, padding to 12 tokens, and padding to 20 tokens. The visualization will use different colors for CLS tokens in blue, SEP tokens in red, regular tokens in green, and padding in light gray. This visualization really helps us understand padding strategies. The first sequence has no padding, just the natural length with special tokens. The second is padded to 12 tokens, adding just enough padding to reach that length. The third is padded to 20 tokens, showing more extensive padding. Notice how the attention mask value is 1 for real tokens and 0 for padding, which is crucial for the model to know what to process. Let's look at building inputs with special tokens manually. Sometimes you need fine control over exactly where special tokens are placed, and the build inputs with special tokens method gives you that control. I'll demonstrate manual special token construction. We'll encode text without special tokens first, then use build inputs with special tokens to add them manually. This gives us precise control over the token structure for both single sequences and sentence pairs. Perfect. When we manually build a single sequence, it adds CLS at position 0 and SEP at the end, just like automatic processing. For the pair sequence, notice we get CLS, first sentence, SEP, second sentence, and final SEP. The structure is identical to automatic processing, but we had complete control over the construction. All our structure assertions pass, confirming the tokens are placed correctly. Now let's dive into token type IDs, also called segment IDs. These are crucial for helping BERT distinguish between different sentences in a pair. Let me show you this diagram that illustrates how token type IDs work. The first sentence and its separator get type 0, while the second sentence gets type 1. Let's create token type IDs manually to understand exactly how they work. I'll encode 2 sentences separately, then generate the token type IDs and see how they align with the complete input structure. Look at how the token type IDs perfectly align with our sentence structure. We have 6 zeros covering CLS, the first sentence, the weather is nice, and the first SEP. Then we have 6 ones covering the second sentence, let's go outside, and the final SEP. This binary distinction is what helps BERT understand which tokens belong to which sentence in the pair. The total length of 12 tokens matches perfectly with our token type IDs. Let me create a comprehensive visualization of token types for sentence pairs. This will show how tokens, token type IDs, and attention masks all work together in a paired input scenario. This visualization beautifully shows the 3 layers of information. The top shows our tokens with blue for type 0 and orange for type 1. The middle graph shows the actual token type ID values, clearly showing the transition from 0 to 1. The bottom shows the attention mask, with dark green for real tokens and gray for padding. We have 12 real tokens out of 20 total positions, with 8 padding tokens at the end. Now let's explore the special tokens mask, which helps identify which tokens are special like CLS, SEP, and pad versus regular content tokens. This is useful when you need to process or filter tokens differently based on their type. I'll get the special tokens mask for a sentence and analyze each token to see whether it's marked as special or regular. The mask uses 1 for special tokens and 0 for regular content tokens. Perfect. The special tokens mask clearly identifies positions 0 and 7 as special tokens, which are our CLS and SEP tokens. All the content tokens in between, including understanding, special, tokens, is, and important, are marked as regular with 0. This mask is incredibly useful when you need to exclude special tokens from certain operations or apply different processing to them. You can also add custom special tokens for domain-specific tasks. This is powerful when you're working with specialized text that needs custom markers. Let me show you how to add entity, number, date, and location markers. I'll create a new tokenizer instance and add 4 custom special tokens for entity, number, date, and location. Then we'll test that these tokens are properly recognized and not split during tokenization. Excellent, we've successfully added 4 custom special tokens, increasing our vocabulary from 30,522 to 30,526. Each custom token got its own unique ID starting from 30,522. When we tokenize text containing these custom tokens, they're preserved as single units, not split into subwords. This is exactly what we want for special markers in domain-specific applications. Let's look at counting special tokens, which helps us understand how many tokens will be added to our sequences. I'll demonstrate how to count special tokens that will be added for single sequences versus pairs. The tokenizer can tell us in advance how many special tokens it will add, which is useful for calculating final sequence lengths. As expected, a single sequence gets 2 special tokens added, which are CLS and SEP. A pair sequence gets 3 special tokens, CLS and 2 SEPs. When we verify with actual encoding, we see the text, testing special token count, has 4 tokens without special tokens and 6 with them, confirming the addition of exactly 2 tokens. The single sequence ends up with 4 tokens total, while the pair has 7 tokens. Now let's explore batch processing with special tokens. When working with multiple sequences at once, the tokenizer handles padding to ensure all sequences in the batch have the same length. I'll process a batch of 3 texts with different lengths. We'll see how padding works to create uniform length tensors suitable for batch processing in neural networks. The tokenizer will pad shorter sequences and truncate longer ones as needed. Look at our batch processing results. We have a 3x17 tensor for our 3 sequences. The first short sequence only needed 4 real tokens, so it has 13 padding tokens. The medium sequence used 7 tokens with 10 padding. The longest sequence actually hit our truncation limit at 17 tokens, using all available space with no padding. This demonstrates how batch processing ensures uniform dimensions while preserving the important information through attention masks. Let me create a detailed visualization of batch padding patterns. This will show how different length sequences are aligned in a batch with padding, making it clear how the attention mask helps the model focus on real content. This heat map visualization makes the padding patterns crystal clear. Green areas show real tokens with attention value 1, while gray shows padding with attention value 0. You can see how shorter sequences have more padding on the right, while longer sequences use more of the available space. Out of 20 positions, sequence 1 uses 4 real tokens, sequence 2 uses 7, sequence 3 uses 17, and sequence 4 uses 6. The attention mask ensures the model only processes the meaningful tokens. Let's work through a practical example of preparing inputs for question answering. This is one of the most common use cases for sentence pairs in transformers. I'll prepare a question answering input where we have a question about who created the transformers library and a context containing the answer. This demonstrates the recommended approach using the tokenizer's call method with proper padding and truncation. Perfect QA input structure. Our encoded sequence has 33 real tokens out of 50 total positions. The decoded sequence clearly shows the question, who created the transformers library, followed by the first SEP, then the context about Hugging Face creating the library, followed by the second SEP and padding. The token type IDs split evenly with 25 tokens for the question segment and 25 for the context segment. The 2 SEP tokens at positions 7 and 32 properly separate the question from the context and mark the end of the context. Now let's explore an advanced technique for handling long sequences with Stride. When your context is too long for a single window, you can create overlapping windows to ensure complete coverage without losing information. I'll demonstrate how Stride creates overlapping windows for a long context. We'll use a small window size of 40 tokens with a stride of 10, meaning each window overlaps by 10 tokens with the previous one. This ensures we don't miss important information at window boundaries. We've successfully created 4 overlapping windows from our long context. Each window maintains the question at the beginning and includes a different portion of the context. Window 1 starts with the field of artificial intelligence. Window 2 overlaps and continues from the deep learning portion with about 3 overlapping tokens, and window 3 moves forward to the translation and summarization part with about 2 overlapping tokens. This sliding window approach with Stride ensures complete coverage of long documents while maintaining context continuity. Here's another visualization showing how Stride windows overlap. Watch how tokens from the end of one window appear at the beginning of the next, marked in yellow to show the overlap. This overlap is crucial for maintaining context across window boundaries. This visualization clearly shows the sliding window mechanism. We created 4 windows total, and the yellow sections show where windows overlap. This 8-token stride means the last 8 tokens of each window become the first content tokens in the next window after the question. This overlap ensures that even if important information falls near a window boundary, it will be fully captured in at least one window. We've covered all unique context tokens across our windows. Let's look at a summary table comparing all the key methods we've learned. Each method serves a specific purpose in the tokenization pipeline. Prepare for model is your go-to for complete preprocessing. Build inputs with special tokens gives you manual control. Get special tokens mask helps identify token types. Create token type IDs generates segment embeddings, and add special tokens extends your vocabulary. Finally, let me create a comprehensive input preparation pipeline that brings together everything we've learned. This function will handle single or paired inputs, apply proper padding and truncation, and verify all outputs are present. Excellent! Our pipeline successfully prepared both single and paired sequence inputs. Single sequences created a 2 by 20 tensor for our 2 test texts, while paired sequences created a 2 by 30 tensor. All required components are present, including input IDs, attention masks, and token type IDs for pairs. Your model inputs are now prepared and ready for transformer model processing. That's all for Chapter 3. You've mastered special token handling, input preparation, and all the techniques needed to properly format data for transformer models. Thank you for learning with me. Welcome to Chapter 4, Vocabulary Management and Customization. In this chapter, we're going to master several crucial skills. We'll learn how to add custom tokens to existing tokenizers, manage and inspect vocabulary additions, train tokenizers from scratch on custom data, convert between tokens and strings, and handle tokenization artifacts and cleanup. This is essential knowledge because real-world NLP applications often require domain-specific vocabulary. Whether you're working with medical texts, legal documents, or social media data, the ability to extend and customize tokenizer vocabularies is crucial for optimal performance. Let me show you the architecture overview. This diagram illustrates the overall structure of vocabulary management in tokenizers, showing how custom tokens integrate with the existing vocabulary and how the tokenization pipeline processes them. Now let's look at the tokenization and detokenization flow. This visualization shows the complete process of how text gets converted to tokens and back, including where our custom vocabulary additions fit into this pipeline. Let's start by importing the required libraries. We'll need transformers for our tokenizers, Matplotlib and Seaborn for visualizations, NumPy for numerical operations, and Counter from collections to analyze token frequencies. I'm also setting up our visualization style to make our plots look clean and professional. Now let's begin with the basics, understanding your tokenizer. We'll start with the simplest example, examining a pre-trained BERT tokenizer's vocabulary. I'm initializing a BERT-based uncased tokenizer and exploring its basic properties. Let's look at the vocabulary size, model max length, special tokens like padding and unknown tokens. Then I'll do a simple tokenization example to see how text gets broken down into tokens. Notice how the vocabulary size is over 30,000 tokens, and the model can handle sequences up to 512 tokens long. Great, we can see the tokenizer has a vocabulary of 30,522 tokens, with a maximum sequence length of 512. The special tokens include padding, unknown, separator, class, and mask tokens. When we tokenize our test sentence, it gets broken down into individual words and punctuation marks, exactly as we'd expect. Now let's explore adding custom tokens with the Add Tokens method. This is incredibly powerful for extending vocabulary with domain-specific tokens. The Add Tokens method takes a list of strings or a single string as the tokens to add. It returns the number of tokens actually added, which excludes any duplicates. Let me demonstrate this step by step. Starting with a fresh tokenizer, I'll first add a single custom token for company names, then add multiple domain-specific tokens like email, URL, phone, date, and currency markers. Notice what happens when I try to add duplicate tokens. The tokenizer is smart enough to only add new unique tokens. We can see the vocabulary growing from its initial size as we add these custom tokens. Perfect, we successfully added 7 new tokens to our vocabulary. The tokenizer correctly handled duplicates by only adding the new token when we tried to add email again. Our vocabulary has grown from 30,522 to 30,529 tokens. Now let me demonstrate how these custom tokens work in practice. I'll create text that contains our custom tokens and show how they're tokenized. We'll verify that each custom token gets its own unique ID and that they're preserved correctly through the encoding and decoding process. Excellent, our custom tokens are working perfectly. Each one is treated as a single token rather than being split up, and they all have unique IDs starting from 30,522. When we encode and decode the text, all our custom tokens are preserved exactly as they should be. Now let's look at adding special tokens with the Add Special Tokens method. Special tokens have specific roles in the model architecture and require special handling. They're different from regular tokens because they often trigger specific behaviors in the model. I'm defining special tokens for a question answering task, including question, answer, context, and entity markers. These will help structure our input for specific NLP tasks. Let's add them and verify they're recognized as special tokens. Perfect, we've added 4 special tokens successfully. Each has its own unique ID starting from 30,522. When we tokenize text containing these special tokens, they remain intact as single tokens, which is exactly what we want for task-specific markers. Let's inspect our added vocabulary with the getAddedVocab method. This is useful for tracking and managing all the tokens we've added to our tokenizer. I'm retrieving all the added tokens and displaying them sorted by their IDs. We can see both the original special tokens like padding and mask, as well as our newly added question, answer, context, and entity tokens. I'm also verifying that the ID mappings are consistent in both directions. Excellent, we have 9 total added tokens, including the original special tokens and our custom additions. All the ID mappings are consistent, meaning we can reliably convert between tokens and IDs in both directions. Now, let's visualize vocabulary growth analysis to better understand how tokenizer vocabularies evolve. I'm creating a visualization that shows how vocabulary grows through different stages, starting with the base tokenizer, then adding domain tokens, special tokens, and finally fine-tuning tokens. This helps us understand the composition and growth pattern of our vocabulary. We can see the vocabulary growing from the base size of about 30,522 tokens through various stages. The bar chart shows the absolute sizes at each stage, while the pie chart reveals the relative composition. Our vocabulary grew by 100 tokens total through domain, special, and fine-tuning additions. Sometimes you need to train a tokenizer from scratch on domain-specific data. Let's explore the train new from iterator method. I'm preparing a training corpus with NLP and machine learning-related sentences. We'll train a new tokenizer from this corpus with a vocabulary size of 5,000 tokens. Then we'll compare how the base and new tokenizers handle the same text differently. Fascinating, our new tokenizer has a much smaller vocabulary of only 276 tokens, trained specifically on our corpus. Notice how tokenization differs between the base and new tokenizers. The word tokenization is split into token and ization by the base tokenizer, but kept as a single token by our new tokenizer, showing it learned from our domain-specific data. Let's explore token-to-string conversion with the convert tokens-to-string method. This properly handles subword tokens and reconstructs readable text. I'll demonstrate various scenarios for converting tokens back to strings, first with simple tokens, then with subword tokens that have the double hash prefix, then with special tokens, and finally with complex wordpiece tokens. This method handles the reassembly of subwords correctly. Perfect, the convert tokens to string method correctly handles all these cases. Simple tokens are joined with spaces. Subword tokens with double hash prefixes are properly merged back together like tokenization from token and ization, and special tokens are preserved as is. Now let's look at cleanup with the cleanup tokenization method. This removes common tokenization artifacts for cleaner output text. I'm demonstrating how cleanup tokenization handles various artifacts like extra spaces around punctuation, spaces before punctuation marks, and issues with contractions. This is particularly useful when generating user-facing text that needs to look natural. Great, the cleanup method successfully removes spaces before punctuation, fixes contractions like changing its to its, and generally makes the text more readable. This is essential for producing clean, natural-looking output from tokenized text. Let's do a comprehensive vocabulary analysis to understand tokenization patterns. I'm analyzing tokenization patterns across our sample texts. We'll look at the most frequent tokens, token length distribution, the ratio of regular to subword tokens, and overall vocabulary coverage. This gives us deep insights into how our tokenizer is actually being used. Our analysis reveals interesting patterns. We processed 550 total tokens with 94 unique tokens, giving us very low vocabulary coverage of just 0.31%. The average token length is about 7.45 characters. About 18% of our tokens are subword tokens with the double hash prefix, showing that the tokenizer is effectively handling word variations through subword decomposition. Now let's build a practical application, adapting a tokenizer for medical domain texts. I'm building a medical domain tokenizer by adding specialized tokens for medical abbreviations like BP for blood pressure and MRI, drug-related placeholders, condition markers, anatomical references, and clinical markers. I'll also add special tokens for patient, doctor, and medical record entities. Let's test it with some medical text to verify our custom tokens work correctly. Excellent, our medical tokenizer is successfully configured. We added 24 tokens total, 19 regular medical tokens, and 5 special tokens. The vocabulary grew from 30,522 to 30,546. When we tokenize medical text, all our custom tokens like patient, symptom, BP, and medication are preserved as single tokens, making the tokenization much more efficient for medical domain texts. Let's dive into advanced token ID management and conversion. I'll demonstrate comprehensive token ID management, including single token to ID conversion, batch conversions, special token ID access, and handling of unknown tokens. This is crucial for understanding how tokens map to their numerical representations that the model actually processes. We can see the complete token to ID mapping system. Regular words like hello map to IDs in the thousands, special tokens like CLS map to low IDs around 100, and our custom tokens get high IDs starting from 30,522. The tokenizer handles unknown tokens by either decomposing them into known subwords or mapping truly unknown tokens to the UNK token ID of 100. Let's compare tokenization efficiency before and after vocabulary expansion. I'm creating a performance comparison between a base tokenizer and one enhanced with domain-specific tokens. We'll measure token count reduction and efficiency improvements when processing domain-specific text. The results are impressive. Our enhanced tokenizer shows significant improvements, reducing the total token count from 80 to 55 tokens. That's a 31% reduction. This means faster processing, lower memory usage, and better model performance on domain-specific texts. Let's wrap up with a summary of key takeaways and best practices. We've learned to use add tokens for domain-specific tokens, add special tokens for task-specific markers, get added vocab for tracking additions, train new from iterator for complete customization, convert tokens to string for proper subword handling, and clean up tokenization for cleaner output. Remember to add domain-specific tokens to reduce overhead, use consistent naming conventions, verify token preservation, monitor vocabulary growth, and test on representative samples. Avoid adding too many tokens which can degrade performance. Don't use conflicting tokens. Always save customized tokenizers. Consider the impact on embedding layers and maintain consistency between special and regular tokens. That's all for Chapter 4 on vocabulary management and customization. Thank you for learning with me. You now have the skills to customize tokenizers for any domain or task you encounter. Let's dive into Chapter 5, where we'll master tokenizer persistence methods. We'll learn how to save, load, and share tokenizers, understand the architecture differences between slow and fast tokenizers, and explore specialized features for sequence-to-sequence models. Here's our tokenizer persistence architecture diagram. This image shows how tokenizers can be saved locally, loaded from disk, or pushed to the Hugging Face hub. Notice the different file formats involved. We have tokenizer config JSON, special tokens map, vocabulary files, and the unified tokenizer JSON. Each serves a specific purpose in preserving the complete tokenizer state. Now let's look at the slow versus fast tokenizer implementation. This diagram illustrates the key architectural differences. The slow tokenizer is implemented in pure Python, making it easier to modify but slower in execution. The fast tokenizer uses Rust under the hood, providing significant performance improvements, especially for batch processing. Both produce identical results, but the fast version offers additional features like offset mapping. Let's start by importing the necessary libraries. We'll need transformers for our tokenizers, matplotlib for visualizations, and some utility modules for file operations and performance testing. Great, our imports are ready. Notice we're importing both the generic AutoTokenizer and specific BERT tokenizer classes. This will let us explore the differences between slow and fast implementations. First, let's explore basic tokenizer saving and loading. We'll load a pre-trained BERT-based uncased tokenizer and examine its properties. I'm loading a BERT-based uncased tokenizer and testing it with a simple sentence to verify everything's working properly. Perfect. We've loaded a BERT tokenizer fast with a vocabulary size of 30,522 tokens. The encoding shows our test sentence converted to token IDs, starting with 101, which is the CLS token, and ending with 102, the SEP token. Now we'll save this tokenizer to a local directory. The save pretrained method returns a list of all files it creates. Let's examine what gets saved. Excellent. We can see the tokenizer created 4 files. The tokenizer config JSON contains configuration parameters. Special tokens map defines our special tokens. Vocab TXT has the actual vocabulary, and tokenizer JSON is the unified format used by fast tokenizers. The vocab file is about 232 kilobytes, containing all 30,522 tokens. Let's load the saved tokenizer back and verify it produces identical results. This is crucial for ensuring our save and load process maintains tokenizer integrity. Perfect. The loaded tokenizer produces exactly the same token IDs as our original. This confirms that saving and loading preserves all tokenizer functionality. Now let's dive deeper into understanding what's actually saved in these configuration files. Let's examine the tokenizer config JSON file to understand what configuration parameters are stored. Interesting. The configuration includes our special tokens definitions, model parameters like max length of 512, and settings like do lowercase being true for this uncased model. The added tokens decoder maps token IDs to their actual token strings. Now let's look at the special tokens mapping to see how special tokens are defined. These special tokens are fundamental to BERT's architecture. CLS marks the beginning of sequences, SEP separates segments, PAD is used for padding, and UNK handles unknown tokens. These mappings ensure consistent special token handling across saves and loads. Sometimes you only need to save the vocabulary without the full configuration. Let's explore the save vocabulary method. The save vocabulary method saves just the vocab files without configuration. This is useful when you only need the token mappings. Notice we only get the vocab TXT file this time, not the configuration files. The vocabulary starts with special tokens like PAD, followed by unused tokens that BERT reserves for potential fine-tuning additions. We've confirmed the vocabulary size matches our tokenizer's vocab size of 30,522 tokens. Let's explore some advanced saving options, including custom file name prefixes and legacy format support. We can save tokenizers with custom file name prefixes, which is helpful when managing multiple tokenizer versions in the same directory. All files now have our custom My Model prefix. This makes it easy to identify different tokenizer versions when you're experimenting with multiple configurations. Let's compare legacy versus unified format saving. Legacy format maintains compatibility with slow tokenizers, while unified format is optimized for fast tokenizers. Notice the key difference. Legacy format saves the vocabulary as a separate vocab TXT file, which slow tokenizers require. Unified format combines everything into a single tokenizer JSON file, which is more efficient for fast tokenizers but isn't compatible with slow implementations. Now let's dive into the performance differences between slow and fast tokenizers. Let's load both slow and fast versions of the same BERT tokenizer and verify they produce identical results. Both tokenizers produce exactly the same tokens. The fast tokenizer maintains a reference to its slow tokenizer class, ensuring compatibility while providing performance benefits. Let's create a benchmarking function to compare the performance of slow versus fast tokenizers across different processing modes. Now we'll run our benchmark on 100 test sentences and visualize the performance differences. Wow, look at these results. The fast tokenizer is significantly faster in sequential mode, and when we use batch processing, the speedup is even more dramatic. This demonstrates why you should always prefer fast tokenizers when available, especially for production workloads. Let's explore special tokenizer features for encoder-decoder models. Encoder-decoder models like BART require special handling for target sequences. The AsTarget Tokenizer Context Manager ensures proper tokenization of target text. The AsTarget Tokenizer Context Manager is particularly important for translation and summarization tasks. It ensures that target sequences are tokenized with the appropriate special tokens for the decoder side of the model. Let's look at preparing batches for sequence-to-sequence models. The prepare sec-to-sec batch method handles both source and target texts together. The batch preparation handles padding and creates separate input IDs for the encoder and labels for the decoder. Notice how the shapes differ. The input has 8 tokens while labels have 12, reflecting the different lengths of source and target sequences. Now let's explore how to register custom tokenizers with AutoTokenizer for seamless integration. The register for auto class method allows custom tokenizers to be used with AutoTokenizer. This is essential when creating specialized tokenizers for your domain. This registration system allows your custom tokenizers to integrate seamlessly with the Transformers library. Once registered, users can load your tokenizer using AutoTokenizer from pre-trained, just like any other tokenizer. Let's discuss pushing tokenizers to the Hugging Face Hub for sharing with the community. The push-to-hub method allows you to share your tokenizer on the Hugging Face Hub. Let's examine its parameters and typical workflow. The workflow is straightforward. After authenticating with Hugging Face CLI login, you can push your tokenizer with a single method call. Once uploaded, anyone can use your tokenizer by simply calling AutoTokenizer from pre-trained with your repository ID. Let's work through a complete practical example, creating a domain-specific tokenizer for medical text. First, we'll generate a synthetic medical corpus for our domain-specific tokenizer example. We've generated 100 domain-specific sentences using medical terminology. This simulates the kind of specialized corpus you might use when adapting a tokenizer for a specific domain. Now let's modify our base tokenizer by adding medical domain-specific special tokens. We've successfully added 5 new special medical tokens. Notice how the tokenizer now recognizes our custom tokens like diagnosis and treatment, preserving them during encoding and decoding. The vocabulary size increased from 30,522 to 30,527. Let's save our customized medical tokenizer and verify it loads correctly with all our modifications intact. Perfect. Our custom tokenizer saved successfully with an additional added tokens JSON file that stores our new special tokens. After loading, it correctly preserves and handles our medical domain tokens. Finally, let's do a detailed analysis comparing different save formats to understand storage implications. We'll create a utility function to analyze the structure and size of saved tokenizer files across different formats. Now let's compare the different save formats visually and examine their file structures. This comparison clearly shows the trade-offs. Standard format includes everything for maximum compatibility. Legacy format omits the unified tokenizer JSON, making files smaller but limiting you to slow tokenizers. Unified format is most efficient for fast tokenizers. Choose based on your deployment needs and compatibility requirements. Let's summarize the key takeaways and best practices from this chapter. We've covered multiple saving methods, each with specific use cases. Save pre-trained for complete functionality, save vocabulary when you only need vocab files, and push to hub for sharing. For performance, always prefer fast tokenizers when available. They can be 10 to 100 times faster. Use batch processing for additional speedup. Remember to test your custom tokens after loading and choose the appropriate format based on your compatibility needs. Let's clean up all the directories we created during this tutorial. Excellent! We've successfully cleaned up all our temporary directories. You've now mastered tokenizer persistence and special features, from basic saving and loading to advanced features like custom tokenizers and hub integration. That's all for this chapter. You've learned how to save, load, and share tokenizers effectively, understand the performance benefits of fast tokenizers, and work with specialized features for different model architectures. Great job working through all these examples. Welcome to Chapter 6, where we're diving into chat templates and conversational AI. In this chapter, we'll master the apply chat template method for formatting conversations, understand template customization using Jinja 2 syntax, implement batch processing for multi-turn conversations, explore advanced features like tools, RAG, and assistant token masking, and finally build production-ready conversational AI pipelines. These are essential skills for anyone working with modern language models. Let's start by understanding the architecture of chat templates. Chat templates are powerful tools that transform structured conversations into model-ready formats. They handle control tokens, role markers, and special formatting automatically, which saves us from manual formatting errors. Looking at this architecture diagram, you can see how chat templates sit between raw conversation data and the tokenized input that models actually process. The diagram shows the flow from structured messages through the template engine, applying role markers and special tokens, all the way to the final tokenized output that's ready for the model. Now let's set up our environment and import the necessary libraries. We're importing transformers, Torch, NumPy, and JSON for our work with chat templates. I'll also check what versions we're running and whether CUDA is available for GPU acceleration. Great, we can see we're running Transformers version 4.56.1 and CUDA is not available, which means we'll be working on CPU. That's perfectly fine for learning these chat template concepts. Let's start with the basic chat template usage. Here we'll see the simplest example of formatting a conversation for a model. We're going to initialize a tokenizer with chat template support using the Zephyr 7B beta model, which has excellent chat template capabilities. Now I'm creating a simple conversation with just a user message asking about the weather. Then we'll apply the chat template to see how it transforms this structured data into token IDs. Let me also decode it back to text so we can see the formatted output with the special tokens and role markers. Perfect. We can see the token IDs that were generated, 18 tokens in total. And when we decode it back to text, we see the formatted output with the user role marker and the end of sequence token. Notice how the template automatically added the proper formatting around our message. To really understand what's happening, let's examine the template structure itself. Chat templates use Jinja 2 syntax to define how messages are formatted. I'll retrieve and display the actual template being used by our tokenizer. Looking at this template, we can see it's using Jinja 2 syntax with conditional logic. It loops through messages, checks the role of each message, and applies the appropriate formatting. For user messages, it adds the user tag, for system messages, the system tag, and for assistant messages, the assistant tag. Each message ends with an end-of-sequence token. There's also logic to add a generation prompt when needed. Excellent, the template was retrieved successfully, and we've confirmed that the getChatTemplate method returns the same template. Real conversations involve multiple turns between users and assistants. Let's handle a more complex dialogue. I'm creating a multi-turn conversation with a system message that sets the context, followed by alternating user and assistant messages about Python programming. Now let's apply the template with different options. First, we'll do basic formatting to see the token count. Then we'll add a generation prompt, which prepares the conversation for the model to generate a response. Finally, we'll get the formatted text without tokenization to see exactly what's being fed to the model. Interesting. The basic formatting gives us 78 tokens, but with the generation prompt added, we get 85 tokens. That's because the generation prompt adds the assistant tag at the end, signaling to the model that it should generate an assistant response. In the formatted conversation, you can see how each message is properly wrapped with its role marker, and the conversation ends with an assistant tag, ready for generation. Let's visualize the processing flow to understand how templates process messages through various stages. This diagram shows the journey from raw messages through template processing, tokenization, and finally to model-ready input. Each stage transforms the data in specific ways, adding role markers, applying special tokens, and converting text to numerical representations. Now let's explore all available parameters and their effects on the output. This is crucial for understanding the flexibility of chat templates. First, let's test the tokenize parameter. When tokenize is true, we get a list of token IDs. When it's false, we get the formatted string. Then we'll examine the add generation prompt parameter to see how it affects the output. Finally, we'll look at the continue final message parameter, which is useful for continuing incomplete assistant messages. Perfect. We can see that tokenize true returns a list with 37 token IDs, while tokenize false returns a string with 109 characters. Without the generation prompt, the conversation ends after the assistant's response. With the prompt, it adds the assistant tag to prepare for generation. The continue final message parameter removes the end-of-sequence token, allowing us to continue an incomplete message. Batch processing is essential for efficiency when dealing with multiple conversations. Let's create a batch of conversations with different lengths and see how the tokenizer handles them. First, we'll process without padding, which returns a list of lists with each conversation's tokens. Then we'll process with padding to the longest sequence and return as a PyTorch tensor for batch processing. Without padding, we get different token counts for each conversation, 10, 17, and 14 tokens respectively. With padding enabled and returning a tensor, we get a batch with shape 3 by 17, where all sequences are padded to the length of the longest one. This is perfect for batch processing in neural networks. Chat templates support various output formats for different frameworks. Let's explore the options, from simple lists to PyTorch tensors to NumPy arrays, and even dictionary outputs with metadata. We'll test each output format. First, the default list output, then PyTorch tensors for deep learning frameworks, NumPy arrays for scientific computing, and finally dictionary output, which includes both input IDs and attention masks. Excellent, we get a list with 13 tokens by default. The PyTorch tensor has shape 1 by 13, suitable for model input. The NumPy array has the same shape, but as a NumPy type. The dictionary output is particularly useful as it includes both input IDs and attention mask, which are both needed for transformer models. Let's explore custom templates by creating our own Jinja 2 templates for specific formatting needs. This gives us complete control over how conversations are formatted. I'll define 2 custom templates, a simple one that uppercases roles and a structured one that uses brackets and separators. Then we'll apply both to see the different formatting styles they produce. Great. The simple template uppercases the roles and creates a clean conversation format. The structured template uses brackets around roles and adds separators between messages. This flexibility allows us to adapt to any chat format requirement. The encode message with chat template method is useful for incremental message processing, especially in streaming scenarios. Let's see how it works for adding individual messages to a conversation. We'll start with a conversation history, then encode a new assistant message both alone and with the history. We'll also demonstrate incremental encoding for a streaming scenario where messages arrive one at a time. The single message encoding gives us 21 tokens. When encoded with history, we still get 21 tokens for just the new message. The full conversation is 51 tokens total. In the streaming example, we can see how each message adds tokens incrementally, perfect for real-time chat applications. Long conversations need truncation strategies to fit within model limits. Let's create a very long conversation and test different truncation approaches. We'll start with a very long message, then truncate it to different lengths. We'll also test truncation with padding for batch processing, ensuring all sequences in a batch are exactly the same length. The full conversation is 260 tokens, but we successfully truncated to 50, 100, and 200 tokens as specified. The batch processing with truncation and padding gives us a tensor of shape 3x50, where all sequences are exactly 50 tokens, perfect for batch processing with fixed sequence lengths. Let's visualize token distribution patterns across different conversation types. This will help us understand how tokens are distributed among different roles and conversation lengths. I'm generating 20 sample conversations with varying lengths and analyzing their token distributions. We'll look at total tokens per conversation, distribution by role, the relationship between message count and tokens, and cumulative token usage. Looking at these visualizations, we can see several interesting patterns. The histogram shows the distribution of total tokens across conversations. The box plot reveals that assistant messages tend to use more tokens than user messages, while system messages are generally shorter. The scatter plot with trend line shows a clear linear relationship between message count and total tokens. The cumulative plot shows how token usage accumulates across multiple conversations. On average, we're using about 59 tokens per conversation, with a maximum of 145 and minimum of 8 tokens. Now let's build a real-world application, a production-ready chat interface class that manages conversations with proper template handling. This chat interface class provides all the essential features for a production chat system. It manages conversation history, trims old messages to stay within limits, handles system prompts, and prepares conversations for model generation. Let me demonstrate its capabilities by creating a conversation and showing how it manages history. Perfect. Our chat interface is working beautifully. The prepared input has shape 1x80, ready for model inference. We have 73 tokens in the current conversation. After adding 15 exchanges, the history was automatically trimmed to stay within our limit of 10 messages plus the system message, demonstrating effective memory management. Let's benchmark the performance of different template operations to understand their computational costs. I'll create conversations of different sizes and benchmark various operations like basic tokenization, adding generation prompts, string output, and tensor conversion. This will help us understand performance characteristics for production deployments. The benchmark results show interesting performance patterns. For small conversations with just one message, all operations complete in under half a millisecond. Medium conversations with 10 messages take 1 to 3 milliseconds depending on the operation. Large conversations with 20 messages can take 5 to 10 milliseconds. String output is consistently the fastest operation, while tensor conversion adds some overhead. These timings are important for understanding throughput in production systems. Let's explore common pitfalls and best practices when using chat templates in production. Understanding these will help you avoid common mistakes. First, we'll test incompatible parameters like using both add generation prompt and continue final message together. Then we'll handle empty conversations and malformed messages. Finally, I'll show you best practices for validation and safe tokenization with automatic truncation. Good, the tokenizer correctly rejected incompatible parameters and empty conversations. Interestingly, it accepted a message without a role field, which means we need our own validation. Our validation function correctly identifies valid and invalid conversations. The safe tokenization function automatically handles conversations that exceed token limits by truncating them. These patterns are essential for robust production systems. Let's explore advanced features by passing custom variables to Genya2 templates for dynamic formatting. This allows us to inject metadata like user IDs, timestamps, and model names into our conversations. I'll create a template that uses custom variables for user ID, model name, and timestamps. Then we'll apply it with these custom values to see how they're inserted into the formatted output. Excellent! Our custom template successfully inserted the user ID 12345, the model name GPTX, and the timestamp. This capability is powerful for audit trails, debugging, and creating rich conversation metadata in production systems. Let's wrap up with a comprehensive summary of what we've learned. We've covered template flexibility with powerful Genya2-based formatting, extensive parameter control for tokenization, padding, and truncation, efficient batch processing for multiple conversations, incremental processing for streaming applications, and production-ready features. The key best practices include always validating conversation structure, monitoring token counts, using appropriate output formats, implementing conversation trimming, testing custom templates thoroughly, handling edge cases, and batching similar length conversations. Common use cases include chatbots for formatting multi-turn conversations, fine-tuning with consistent data formatting, streaming for real-time responses, analysis of conversation patterns, and translation between different chat formats. That's all for Chapter 6 on chat templates and conversational AI. Thank you for joining me on this deep dive into chat template functionality. And that concludes our comprehensive exploration of chat templates. See you in next video.